Hi, in this session, we will design a small and simple finite state machine project. Although we will cover finite state machine topic little later, but this is just to give you a little brief that how you write VHDL designs in Quartus Prime and then implement it on FPGA board. So what we will do that we will develop a simple traffic light using finite state machines. We will write VHDL code for this and then we will implement it on FPGA as well. So for traffic light, we will have three lights, red, yellow and green. Red will turn on for 2 seconds. Yellow will turn on for 1 second and green will turn on for 3 seconds. So our one complete cycle will be of 6 seconds just for this design. So how we will do that? First, we will define a data type and signal for this traffic light, which will have three values, red, yellow and green. Then we will write a process block for generating 1 second signal. Basically, we convert 50 megahertz clock into 1 second signal. And then we will count it from 1 to 6 seconds. And when this signal become 1, our red state will trigger. Then it will hold for 2 seconds, means when the signal become 3, then our state will change to yellow. Then hold again for 1 second, means when this signal become 4, then we will change our state to green. And this cycle will run in an infinite loop. So this is the plan for this project. So let's jump to the Quartus software and start developing it on FPGA board. Okay, so we will start Quartus Prime software. So go to start and write Quartus. We will open this Quartus 2 10.1 web edition. We are selecting this version because we are working on Cyclone 2 device and recent Quartus release do not support those old FPGA devices. So we have this version here to work on Cyclone 2 devices. But steps are almost same if you are working on the recent release from Quartus. So once you open Quartus, you will see this create a new project wizard. Now click on this button. Okay. So this window is new project wizard. So once you see this window, just click on next. Now at this page, we need to give project directory name and your project name. So give it. So click on these three dots here. Now select the respective folder where you want to save your project. Suppose I want to save my project in this projects folder and I want to create a new folder for this new project. So here is a button, make new folder. So click on it and give it some name. Suppose this project is traffic light. So give some name, traffic light. Now copy this because we will use this as a project name. Okay. Now select it and click on OK. And now it is asking for your project name. So just copy your project name here. So this is traffic light. Now once you finish up with this, just click on next. Now this is add file section. So if you have any existing file which you want to use in this project, then you can add that particular files from this page here. But because this is our fresh project and we do not have any file to add at the moment, so we will click on this button next. Now this is important page here because here you will select your FPGA device in which you are working. For example, I am working on Cyclone 2 device. So I will select this Cyclone 2. Now you can see there are many FPGAs listed here for this Cyclone 2 and we need to select our FPGA. So you can select it from this big list or you can filter down this list by using some additional filter and these are listed here. For example, my package is FPQFP. So I will select this, then pin count, then my FPGA has 208 number of pins. So I will select it. Now it is asking for speed grid and that is 8 for my FPGA. So you can see that we have only 4 FPGA device with these additional filters. So it is shorten list to select your FPGA. For example, my FPGA is EP2C5Q208C8 and this means that we have 2C, this is Cyclone 2 device, 5Q208. So 208 is number of pins, Q is your QFP package, and C8 is your speed grid. So that's why it's 2C5Q208C8. So select my device and click on next. Now at this page, you can select your simulation tool if you have more than one simulators. For example, there are a couple of simulators listed here. For example, you are using this QSTES simulator. Then you can select it from here and then your SDL language. For example, Verilog SDL if you're using Verilog. If you're using VHDL, like in our case, we will select this VHDL. But for this project, we are not doing simulation. So you can leave it as default and just click on next. So this is our summary page and it is showing whatever you have selected during the previous steps. For example, this is our directory location. This is our project name, traffic light. We have selected Cyclone 2 device and this is our FPGA device name. We have selected QSTES simulator as a simulation tool and VHDL as in language. So this is just a summary page. So just review it and then click on finish. Now, once you click on finish, then Quartus will create a project for you. So you can see that Quartus has created this traffic light project for you here. Now this is hierarchy view. You have more views like files. So you can see this is empty here because we have not added any files and we have not created any files yet on this project, right? So this is blank at the moment. Now just switch back to the hierarchy view and now create a new file. So for that, we will go to this file tab and click on this new button, or you can just directly press Ctrl N from your keyboard. Okay. So once you click on that, you will see this big list here. Now you are working on VHDL. So click on this VHDL file and then click on OK. Now this is your VHDL editor where you will write your VHDL program. This is the project navigator where all the files will be listed here, which you are using for this project, right? And this is task view where all the options are listed which are needed for your project. For example, this is compile design. This is for check your syntax and for check your RTL viewer, for pin planner, and there are many tools listed here. But few of them which we will be using in this project, this is number one, this is analysis and synthesis. Next is pin planner because this will tell the Quartus software that what FPGA pin will be connected to the what pin of your VHDL design. Next, we will use this fitter place and route option and we will use this assembler. So this will generate the binary file for your FPGA, which you can program in your FPGA device. And finally, we will use this program device or open programmer to program our FPGA device. So these are few of the tools which we will be using in this project here. And for the other tools, we will be learning them in a separate session. Now go back to the editor and the first step what we will do that we will save this project because you can see that this is named as vhdl1.vst that Quartus give by default when you create a new file. So first we will save this file with a better name. So click on file and click on save as. Now locate your project directory. So my project is this traffic light. So select it. Now I want to save all my VHDL files in one single folder. So for that, I will create this new folder and I'm giving this source src. Okay. So I know that all of my VHDL files or VHDL source are located in this folder only. So select this and give the name traffic light and click on save. So now you can see that our file is saved as source traffic light.vsd. Now we will start writing our VHDL code. So first we will give the library and package declaration. So give it library IEEE use IEEE.std underscore logic underscore 1164.all. Now give the entity declaration. So give it entity traffic light is port now and entity and traffic light semicolon. So we have created this entity body here and now we will define all our input output ports in this section. So what we will have, so we have clock as an input, so give it clock in std underscore logic. Now we have three LEDs, that is red, yellow and green, right? So you can create three separate outputs. For example, LED1, that is out std underscore logic, LED2 out std underscore logic, and LED3 out std underscore logic. So you have one input as in clock and you have three outputs, that is LED, right? Now there is one more way to declare these three LEDs. How? So I will write this as an LED. Now this is out and I'm saying that this is std underscore logic underscore vector. And this is 1, 2, 3. So what I am saying that I have a LED as an output and this output is having three elements inside it. That is LED1, LED2 and LED3. So this port is equivalent to these three LEDs output. So either you can use three separate lines to define these LEDs as an STD logic output, or you can define this single STD logic vector signal as an LED. And in this LED output, you have three elements inside it. Okay, so these three line of code and this one single line of code is equivalent. Okay, so we will use this line LED as an output, STD logic vector 1, 2, 3, and we will remove this. Okay, so this is our entity declaration. Now it's time for the architecture declaration. So write it. So write architecture behave of traffic light is begin and behave. So what I have did, I have just defined the body of this architecture. And now we will write our functioning for our project. Okay, so first what we will do that we will create a process which will give us 1 second signal, because our traffic light will drive based on this 1 second signal. Remember, as we said, that red light will turn on for 2 seconds, then yellow light will turn on for 1 second, and then green light will turn on for 3 seconds. So first we will create this 1 second signal. So for this we will use a process block, and this will be a registered process block. So write it. So give some name to this process. Suppose my process is process clock. Now process. Now because this is a registered process block, so we will use clock as a sensitivity list. Now begin and end process. Okay, so this is the body for our process block. Now write the condition for a registered block. So give the condition if rising edge of clock, then and in the last and if. Okay, so this is the body. So we are using this rising edge of clock. That means we will be getting the registers version of our signal, and this will generate a flip-flop in our physical design. Now this is important step, because we are using 50 megahertz of clock frequency on our FPGA board, and we need to generate 1 second signal from it, right? So what we will do that we will use a counter that will count from 0 to 50 million times, so that we can get our 1 second signal, right? So write the code for this. So what I am writing that if our counter is greater than 49,999,999. So this number is actually 1 less than 50 million, because we are starting our counter from 0, not from 1. So we are counting this up to this number, not 50 million exact, right? So if counter is greater than this, then what will happen? Then our counter will reset to 0. So give it counter should be 0. Else, now what will happen if counter is less than this value? So we want to increase our counter by 1, right? So give it, so counter should be counter plus 1 semicolon. Now we are using this counter here as a signal, but we have not defined it in our VHDL code, right? So first we will define this. So write signal, now counter, and this is integer type, and it is having the range from 0 to 50 million. So 50, 0, 0, 0, 0, 0, 0, semicolon. Now we are creating another signal that will count each second based on our 1 second signal, right? So suppose this is a signal named as sec, and this is integer type and having the range from 1 to 7 semicolon. Just correct it, integer range from 0 to 50 million, right? So this is the right syntax. Okay. Now go back to our process section. So we are saying that at every rising edge, our counter will increase by 1. And if it is reaching to 50 million or this 49,999,999 number, then it will reach that to 0, right? So we have written all the conditions here. So just terminate this if condition by and if. So this is completed now. Now the second part comes where we will use another if condition that will count our second signal from 1 to 6, right? And based on this second signal, we will drive our LED outputs like red, yellow and green as we discussed. So we will write that if the second greater than 6, then what will happen? Our second should be reset to 1, right? Else what will happen? Second should be second plus 1. Okay. And if. So what we have did that this counter signal, this is counting from 0 to 50 million times and it is giving us 1 second cycle. And we have this another condition. This is driving our second signal. But here is the problem. Because what will happen that this second signal will count and increase its counter at every rising edge of clock, right? At this, because we have this condition. But what we want that we want to increase this signal at every second, right? So we need to write this inside one additional condition. So we will use that ELSIF instead of else, and we will say that else if counter is equals to 0, then this condition will happen. Okay, so this second will increase by 1. Now this counter will be 0 at every 1 second. Why? Because this counter starts counting from 0 and it will increase by 1 at every rising edge of clock signal. So it is increasing 1, 2, 3, 4 up to 49,999,999. And because we have this condition that is counter is equals to 0, so this condition will only met when this counter counts 50 million times, and that will be our exact 1 second, right? So at this point of time, we will increase this second by 1 factor. Okay. So it will start from 1 and it will go up to 6, right? Because as soon as it reaches to number 7, it will reset to 1 again, right? Because we have this condition here. When sec is greater than 6 means when it will touch 7, it will reset to 1 again. So it will count from 1 to 6. Okay, so that's one part that is completed now. So we will go back to our architecture body. So what we have did, we used 50 megahertz of clock cycle and we converted it to 1 second signal, right? Then we counted our 1 second signal up to 6 times. So now it's the time to drive your LED outputs, which is red, yellow and green based on this second signal, right? So we will write another process for that, which is for state diagram. So give some name to this process. Suppose this is state process, right? Now process, again, this is a registered process block. So we'll use clock as a sensitivity list. Now begin and end process. Okay, so we have created the body for this process now. Now write the basic structure for this register process block. So write if rising edge of clock, then and if. Okay. Now before we start writing this state machine for our project, let's define a new data type for our traffic light so that we can use it. So we will define it inside this architecture and begin section. So write type TL for traffic light. So give type. So this is TL type is red, yellow, green. Okay. So we have this TL underscore type as a new data type and it will have 3 values. This is red, yellow and green. Okay. So we have defined the data type. This is the new data type for this project. And now we need to create a signal for this data type, right? So create signal and give it some name. For example, traffic light. So this is TL and now this is TL underscore type semicolon. So this TL signal will have 3 values, that is red, yellow and green. Okay. Now we will go back to our state process so that we can define our state machine, right? So first we will write the basic structure of our state machine. And for that purpose, we generally use case statement, right? So we will use case traffic light is, now define the state. So we have three states, right? So first state is red. So when red, what will happen? We will define it little later. Just we are writing the body here. So red, now yellow, then it will do something. And when green, then it will do something. And in the last, when others. Okay. So this is mandatory to write others when you're working with the case statement. Okay. Because these three states, that is red, yellow, and green, these are known states. But if in any situation your device jump to some unknown state, maybe because of some hardware issues or glitches, then this other sections will help you to reset your condition. Okay. So what we will do when this other condition will meet, we will jump to some known state. That can be anything. That can be red, that can be yellow, that can be green. For example, in our case, we want to jump to this red state, was in safe side, right? So when others, then our TL will become red. Okay, so we have reset this TL signal to the red state, and we want that our red LED should on. So our LED output will be 100. Don't worry, I will explain this number in some time. So now let's jump back to this when red state is happening. Okay. So what will happen that when you are at this red state, so your red LED should on and your rest two LEDs should be off, right? And suppose our LED first element is red, second element is yellow, and third element is green. So our LED first element should be 1, right? LED 2, that is our yellow LED, that should be 0, right? And LED 3, that is our green LED, that is again 0, right? So this will be our output. Now because we have used LED as a vector data type, that is std underscore logic underscore vector. So we can write this LED as an output like 1 0 0. So this 1 is our red LED, this 0 is our yellow LED, and this 0 is our green LED. So this single line is equivalent to these three lines here. Okay. So either you can use these three lines or you can simply use this one single line. Okay. Both will do the same thing. Okay. So we will use this single line statement, that is LED gets the value of 100. So we will remove these three lines. So let's delete it and we have this one single statement. Okay. Now we will define that when we at this red state, then what will be our next state, right? So after red, the next state will be yellow. But when? After 2 seconds, right? And that is we have defined for our project, like 2 seconds for red, 1 second for yellow, and 3 seconds for green, right? So write that condition that if this second is equals to 2, then what will happen? Our state will change to yellow, right? And if so, we have finished this red state. Now let's move to the yellow state. So what will happen at yellow state? So our yellow LED should on and rest two LEDs should off, right? So right LED should be 0 1 0, right? So this is red, this is yellow, this is green. Okay. So we have met this. Now semicolon, and now we will write what will be the next state. So what is next state after yellow? That is green, right? So write it. If second is equals to 3, then our next state means traffic light should be green and if. So now why we have used 3 seconds here? Now second is equals to 3 because for 1 or 2 seconds it will be at red state and then second will be 3. So this is 1 second after red, right? So we have used this second equals to 3, then next state will be green. So next jump to the green state. So when green, now our LED output will be 0 0 1 because this green LED is on and rest two LEDs are off. Now we will define that what will be the next step or next state, right? So write it. What if sec is equals to 6, then what will happen? The next state will be again red. Okay. Now and if. So what is happening that when you are at this red state, then red LED will on and it will wait for 2 seconds. And after 2 seconds, it will jump to the yellow state. And when you are at yellow state, then your yellow LED will turn on and it will wait for 1 second. 1 second, why? Because 2 seconds is already completed here. So when we jump from 2 to 3, that will be exact 1 second, right? So this means that 2 seconds for red, 1 second for yellow. And after that, we will jump to this green state after 1 second of yellow. Okay. So when this green state comes, then our LED output will be 0, 0, 1. So this is red, yellow and green. And when this completes one cycle and it will wait for the 3 seconds on the green state, then it will jump to the red state again after 3 seconds on green, right? So this is happening in the loop because from red to jump to yellow, and then from yellow you jump to green, and from green you jump to red again. So this is red. Okay. So you are doing it on the cycle. Okay. So this is our VHDL code. So I think that everything is completed. Nothing looks wrong with this code. So let's save this code and compile it. So you will see this button here for this compilation. So just click on it. And now Quartus is compiling your VHDL code. So as you can see that it come up with some syntax error. So click on OK. We will click on this error and it will jump to the problematic area of your code. Okay. So I already figured out that what is the problem. We have used this case statement, but we have not terminated it. So we need to terminate it with AND case statement. Okay. Now save this and compile again. So you can see that full compilation was successful and there are few warnings. So we will ignore these warnings at the moment because few warnings would be related to your timing constraints because we have not defined it yet. Few warnings would be related to net list because we have not defined it yet again. And we will be doing this in some time. So we are just ignoring these all warnings at the moment. Okay. So we can see that our VHDL code is successfully compiled and that is everything is okay in this code, means there is no syntax error, right? Now the next step is pin planner. So you will see this button here. So you can open this pin planner from this button here, or you can also open it from this taskbar. Okay. So here you will see this pin planner. So you can double click on it, or you can just simply click on this button. Okay. So I will open it. Now this is your FPGA view. Okay. So this is Cyclone 2 device and this is your device name, which we have selected during the initial step of defining this project. Now this FPGA is having the 4 sides. So this is side A, this is side B, this is side C, and this is side D. Each side is having some specific number of pins, right? So you can see there are number of pins listed at this side, same at this side, same at this side, and same at this side. So if you zoom it little, this particular view from here, and let's zoom in little, so you can see these numbers here as well. For example, so this is your starting point and your pin count starts from here. So it is starting from 1. Let's take the pen tool and let's slide it little so you can see all the pins listed here. So this is side A and it has total 52 number of pins on this side. So this is side B and the pin count start from 53 to up to 104. And this is side C up to here. And this is your side D. So you can see that total number of pins are 208. Okay. So let's zoom out. Now look at this window here. So you can see that Quartus already listed all the input output ports here. Like you have one clock signal and you have one output, but that is LED steady logic vector signal. And this is having 3 elements inside it. So Quartus already differentiated it for us. So this is LED1, this is LED2, and this is LED3. Now what we are doing here, that we are defining that which port of your VHDL project is connected to which pin of your FPGA device, right? So that's what we are doing here in this window. Okay. So for example, this clock input. So you can see this is a clock signal. This is input, and there are some fields. These are blank here, and we are going to fill these informations. And for this data, you need to look into your board specification. So you need to see that in your FPGA board where this clock input is given, right? For example, for my FPGA board, this input pin is connected to pin number 23. Okay, so write pin underscore 23. So this is the way how you define your pin number. So this is pin underscore then your FPGA pin number. Like for example, in my FPGA board, my clock frequency is connected to this pin number 23. Okay, so I have written this pin number 23. Okay, now we are having three outputs and we need to connect each LED to the FPGA pin, right? So in our case, our LED1 is connected to pin number 15. So write it 15. Next LED is connected to pin number 13. So pin number 13. And third LED is connected to pin number 11. So pin number 11. So our clock is connected to pin number 23. So if you click on it, and it will highlight the respective pin in the FPGA view as well. So for example, I have selected this clock as an input. So this is highlighted that this is pin number 23, right? So you can see this is pin 23. And if I zoom it little, so you can see that this is connected to pin number 23. You see this blue border here. So this is defining that this particular pin is actually selected. Okay. So same way, if you select this LED1, then it will highlight this pin number 15 because this is connected to pin number 15. Okay. Now if you select LED2, so this is pin number 13. Okay. LED3, this is pin number 11. Likewise. Okay. Now this is important thing, that is input output bank. So each FPGA is having number of banks and each FPGA pin must belongs to some specific input output bank. So for example, we have selected these 4 pins of our FPGA, right? And it is saying that all these 4 pins are connected to the IO bank number 1. And this is having the default 3.3 volt LV TTL as an input standard. For this FPGA, this is standard and fixed. But if you are working on some recent FPGA, you can select the voltage on this. And again, this must be specified by your FPGA board manufacturer. Okay. But for our device, this is pretty standard. Okay. So let's zoom out little and close this. Well, important note here that you do not need to save this pin planner after making the changes. And if you notice, then there will be no save button here. Why? Because this pin planner automatically saves whenever you make any changes on this view. Okay. So if you change this clock or if you change any LED output pin, then it will automatically save after you make any changes in this window. Okay. So you do not need to save it. Just specify the thing and then close the window. And now it is already saved for you. Okay. Now, because we have changed the pin planning for this project, that means we need to recompile our design. So you see in this task view, everything is defined as a question mark. Okay. So we will run the compiler once again. So click on this play button to start compilation and it will start compiling. Okay. So it will take few seconds to complete and it's done. So it is full compilation was successful and now there are 8 warnings. Okay. So click on OK. Now this is the time when you program your design into the FPGA board, right? So for this purpose, we will use this programmer. Okay. So there is a button so you can directly open it from here or you have this same option here as well. So you can see this program device, open programmer. So you can open it from here or from here. Okay. So just click on it. Click on OK. Now this is your programmer window. I will just make it little wide so you can see it properly. So this is your programmer. This is your traffic light.sof file. So this is your binary file which will be flashed or programmed into your FPGA device. Okay. And this is your device name, that is EP2C5Q208. Checksum, that is for some validation. User code FF, that means none. and make sure that your program or configure button is ticked like here. Okay. Now this is your progress bar. So once you start flashing your program into the FPGA board, you will see the progress here. Okay. And this is your hardware setup. Now this is showing that USB blaster is already connected. But in your case, if you don't see anything here, then just click on this hardware setup button and your programmer should be listed here as an USB blaster. Okay. If you are not seeing your USB blaster here, then there might be a connection issue. So make sure that you have connected your USB with your FPGA board, or it also may be a driver issue. So if this is the case, then update your drivers and then check again that your device is listed here or not. So once you see your device listed here, just select it and then click on close. Okay. Then you should see your USB blaster listed here. Okay. So once you see it, now click on your bandwidth file and you will see this start button flashing here. Okay. So just click on this start button and you will see the progress. So this is very quick. That is 100% successful. This means that we have successfully flashed our program into the FPGA board. So next we will jump to the FPGA device and we will see if our program is working well or not. So let's jump into it. So this is our FPGA board. Now suppose this first LED is our red LED, this LED is yellow LED and this LED is green LED. And we have programmed it like 2 seconds. It should be in red state. Then it will jump to the yellow state for 1 second and then it will jump to the green state for 3 seconds. Means 2 second red, 1 second yellow and 3 second green. So let's see if this is happening or not. So this is red, now yellow, now green. So red again for 2 seconds, now yellow, now green for 3 seconds. So this means that our VHDL program is working well as a traffic light and we have developed it using a finite state machine system. Okay, so that was our demo for this project. Hope you liked it and learned from it. So you see that first we converted 50 megahertz clock into 1 second signal and then we counted it for 6 seconds. And finally, based on our project specification, we change the state at specific time and we get our final traffic light where red is on for 2 seconds, yellow is on for 1 second and green is on for 3 seconds. Just a note, because I am using Cyclone 2 device, so I have used this Quartus old version, but steps are almost same for design and implementation on Quartus. In the future sessions, we will be covering more such projects and we will implement them on FPGA board as well. We will see different real life issues like bouncing of switch and we will learn that how to solve them. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video and don't forget to share. Thank you for watching.